Hey everyone, welcome to another video on machine learning. Here we are going to learn about Softmax. And Softmax is an activation function that is similar to ReLU, rectified linear unit, and Sigmoid. But Softmax formulates on the thing called universal natural limit. So in simple terms, it's just E. We have seen this exponential thing, right? E, which is called the natural limit that anybody can reach. So let's say I took some loan. Let's say I took 1 rupee loan for an interest rate of 100%, and the time I have got is like 12 months. So in 1 year the amount will be like 2 rupees. Let's say I compounded this annually. I compounded this one, let's say for 6 months, or 6 months I compounded this thing. So that will be like 1.5. Yeah, this will be multiplication, and this will be 1.5. So that is the case here. And if I compound this annually, if I compound this thing monthly, so for each month we'll have 12 months, and the formula will look like this. So the first principle of E, according to Google and some AI, is introduced by Bernoulli. We heard about Bernoulli's principle in physics class. He came through the same analogy, but modern computers use something different. The representation looks like this: 1 by 0 factorial plus 1 by 1 factorial up to the point we need it. And this calculation is embedded on the silicon chips we have here on our laptops, computers, and several other systems. They'll use some sort of computer, and that system something called Chorus or something. Yeah, I forgot. But this will do the calculation for us. Now coming to the main point, what's softmax? So let's say you went to a marriage, and in that marriage you have different set of items, and you need to pick one from these things. Let's say we have three items. Let's call them one, two, three, or something like biryani, beverage, or some paneer. So if we what we do is we apply this exponentiation of e for each value, and after that we'll do the sum of these values we got. Let's call it e power s. Yeah, mathematically this is wrong, but let's call it e power s. This is the sum of it, and what we'll do is we'll divide each of the value exponential value we got with the sum, and whatever sum that is the maximum here, we'll choose that. And through vigorous training and adjusting different weights, adding different kinds of algorithms on top, today we have achieved LLMs. And LLMs also follow the same thing. They'll predict the next token based on the softmax we got. Let's say this cat is, and we'll have a set of choices we'll get that are aligned with this is. This cat is, like, this cat is purring, this cat is annoying, and this cat, yeah, let's call it some beta or alpha. So we'll calculate the softmax and check what matches this the best. And this is how LLMs predict the next token that we need using softmax. And softmax is quite universal. For this, let's solve the problem. And there is another edge case we have. Let's say the array got values like this: 10,000, 20,000, somewhere like that. If we try to do something like this, e power 10,000, the machine will scream and say, man, I don't want to do this. There is like an insane amount of calculation that will start from 1 by 1 factorial to 1 by 10,000 factorial, and that will eventually reach infinity, and that will break the system automatically, and we'll get integer overflow errors. So for this we'll use this trick, and that's called a stability trick. What we'll do is we'll pick the max from this array, whatever max we can get, and we'll just subtract the max from each value. So we'll end up with values like these, small and simple, and sometimes negative values, and negatives won't matter that much in exponentiation. And eventually applying this will end up with some sort of value, and that sort of, and with that value we have to live. And most likely, in a basic sense, the predicted output won't be correct. Yeah, it is not correct, but computer scientists and so many researchers applied different kinds of algorithms, added cache on top. They use different kinds of vocabulary just to give us the sense that we are talking to a human instead of a machine, and show us that it won't make that many mistakes with the right amount of calculations. So this is about softmax. In the traditional sense, it is an activation function. It is mostly used in LLMs, CNNs, convolutional neural networks, and mostly in predictions too. So softmax is quite a useful concept and universally accepted. So let's solve a problem now. Before that, let me erase this thing. So eventually we have to apply that NP trick. I mean the stability trick I have discussed about. So let's apply that stability trick. So using NumPy, I can just do this. So what I'm doing is from this whole array, I'm just subtracting the max of the whole array, and NP works with it. And I, on top of this, I'll add this. We'll do the e power exponential value, and some may get some small doubt like, what if maybe that value may change if I minus these things? No, they stay stable. Let's say if I have e power x, and if I take away 5 from this, that is the max, they will be the same because it's e have an ending. Then that's 2.718, and this thing you can find in the examples. Here e power 1 is 2.718, and e power 0 is 1. That's the constant, and constants are quite useful when you're dealing with things like this. And we're going to return the value we need. That will be exp divided by the sum of exp, sum of the whole exponentials. And I'm going to round this off to 4 according to the problem. Let's round this off and run this. Let's hope this works. Yeah, and this is working. So thank you for watching. After this we are going to discuss other things that are in this module, and if I get a good amount of views, and yeah, please do subscribe and like and share this. If I get good amount of views, I'll get out of this neat code platform and explore other things as well, maybe like code wars, just to learn machine learning and go through the basics again. But whoever watching this, thank you for watching. You made my day, and bye. This is Databots. Please keep watching.